This symposium has been put together by the Deep Dementia Phenotyping, or DEMON network, and I'm the co-lead of the imaging working group of the DEMON network. So please do come and ask questions about that later. We'd really like this symposium to lead to something sort of concrete and ongoing. So please come and talk to us after the symposium. Have a chat to myself or any of our wonderful panel of speakers and chairs here as the rest of the meeting goes on. We will have our presentations and try and get through them fairly quickly so we leave some time for discussion at the end. So please put Q&As in the phone app, and we will collect them all together and answer them in the panel session at the end. I will leave Aman to introduce herself and our first speaker.
Good morning, everyone. I'm Amanpreet Badwar. I'm a co-organizer of this symposium. I'm an assistant professor at the University of Montreal in the Department of Pharmacology and Physiology and Biomedical Engineering. And my own expertise is combining imaging with multi-omics, so like the molecular omics, in search of dementia biomarkers. So after that quick intro on myself, I'm actually very happy and excited to introduce Professor Rose Bruffarts. Professor Rose Bruffarts is a tenure-track assistant professor in the Department of Biomedical Sciences at the University of Antwerp. She's a neurologist seeing people with various types of dementia at the University Hospital of Antwerp, and she has a wealth of research experience developing biomarkers for neurodegenerative diseases. In particular, Rose's work focuses on computational models of disease, and particularly relevant for this symposium, she works on how to translate AI models for diagnostic use in memory clinics. Rose is currently leading a project to develop guidelines for implementing AI for neuroimaging in memory clinics through the Deep Dementia Phenotyping, or the DEMON network. Welcome, Rose.
Hello, good morning, everyone. I am happy to be here to give you my neurological perspective of AI for neuroimaging in the memory clinic. I have no competing interests. So sometimes if you look at journal headlines, it seems that medics will be replaced by AI tools quite soon. Now, actually, when you think of it, there's a lot of AI research in the medical field, but as clinicians in the memory clinic, we don't really get a profit from all these breakthroughs. There are not many AI tools currently being used in memory clinics around the world. During my talk here, I would like to explore the reasons behind this so-called AI chasm. So from an outsider's perspective, it seems quite obvious that we may be able to improve our diagnostics in the memory clinic using AI, because we have access to enormous amounts of medical data being generated in memory clinics. For instance, structural MRI is being used in almost every patient. We could bank on increasing computing speeds, and also, as you know, there have been huge advances in image recognition algorithms over the years. So combining this, why not use AI tools for diagnostics in the memory clinic? Before getting into this, I would briefly like to rephrase our question. If we would be using AI tools in the clinic, what would we actually be using them for? What would be the main benefit for neurologists in the memory clinic that AI tools could play a role in? I would hence like to tackle this question to discuss the unmet needs of neurologists in the memory clinic. Actually, in the outpatients we see, this may be surprising to you, but in up to 20% of the patients, we actually give them an incorrect diagnosis. In the memory clinic, there are some commonly encountered types of neurodegenerative disease, and I would briefly like to take you through them to explain how it can be that we arrive at the wrong diagnosis so often. So first, there's Alzheimer's disease, which is the most common type of neurodegeneration. This is mainly presenting with memory decline, but patients may also exhibit language disorders or behavioral changes. Next is frontotemporal degeneration. People typically have behavioral changes and language problems, but also sometimes they may suffer from memory decline. And third, one of the more common types of neurodegeneration is Lewy body disease, where typically patients present with visuospatial cognitive changes, but also memory decline and Parkinsonism may occur. So as you can tell from this slide, there's also some overlap in the clinical symptoms between these three most common types of neurodegeneration. And when you look at the types of hypometabolism in these three types of neurodegeneration, you can see that the patterns of hypometabolism are somewhat distinctive, but there's also a lot of overlap. So this is one of the challenges that we're faced with in the clinic. But on the other hand, you must realize that these three common types of neurodegeneration are neuropathologically very different, and they're entities requiring in the future probably different disease-specific treatments, hence the very important need to differentiate between them in vivo. Let me briefly discuss the current typical diagnostic trajectory in the memory clinic and how structural MRI comes to play here in our everyday clinical practice. So first, when a patient presents to the memory clinic, the first goal of the first consultation is to objectify a suspicion of neurodegeneration. The tests which are ordered at this stage are neuropsychological testing and structural MRI. So at this stage of the investigation, these structural MRIs are actually not primarily diagnostic, but they're mainly used to rule out space-occupying lesions and also to identify cases of vascular dementia, as you can see here on the right-hand side. In cases of neurodegeneration, you can sometimes see atrophy patterns on your structural MRI, but in early stages, the MRI scan can often still be quite normal upon visual inspection. After this first round of tests, if the suspicion of neurodegeneration is confirmed, we go on to the next stage, and at this next stage in the memory clinic, we try to identify the most likely cause of the neurodegeneration. So for this, we use the collection of cerebrospinal fluid. We perform PET scans or SPECT scans, for instance, amyloid PET, and in selected cases, also genetic testing will be performed. So after this diagnostic trajectory, how come up to 1 in 5 patients get misdiagnosed? Well, the most likely reason for this is that except for Alzheimer's disease, robust biomarkers for sporadic neurodegenerative diseases are lacking. So what we're actually looking for in the memory clinic are in vivo biomarkers which can differentiate between neurodegenerative diseases. Here, sensitive tools like AI in neuroimaging may be able to play an important role. So together with the Deep Dementia Phenotyping Network, or the DEMON network, we try to map these unmet needs and to compare them to the current research efforts. For this reason, we performed a systematic review. You can find a QR code linking to the preprint here, and on this map you can see the distribution of DEMON network members all over the world. This systematic review was led by Robin Borchert from Cambridge University. In the review, we included AI papers on patients with Alzheimer's disease, frontotemporal degeneration, Lewy body dementia, mild cognitive impairment, Parkinson's disease and related disorders, Huntington's disease, vascular dementia, or all-cause dementia. The neuroimaging modalities which we included were MRI, PET, SPECT, EEG, and magnetoencephalography. We identified 252 research papers between 2000 and 2021, and as you can see here, the number of papers on this topic is steeply rising. When looking at the neuroimaging modalities used and their frequencies, it is not surprising to see that structural MRI was the most frequently used. In 32 cases. Only 26 studies used functional MRI, and a similar number used PET or EEG. Just to give you a feel of the reported accuracies, in the case of diagnosing mild cognitive impairment and Alzheimer's disease from structural MRI, the reported accuracies were between 60 and 99%, with lower accuracies when a disease was in an earlier stage. What we noted in the systematic review was that heterogeneous diagnostic criteria were used for Alzheimer's disease, and a lot of AI papers are talking about early diagnosis, while they don't, or they variably define what early diagnosis actually means. When looking at the source data for the AI papers in the systematic review, we noted that the ADNI dataset was most frequently being used in over 70% of the studies. While, of course, it's an impressive dataset, this over-reliance caused some concerns, and also the reuse of the dataset causes a lack of diversity of the subjects that are being studied. Another thing which we observed was that there was a lack of multi-class designs where MRIs were being classified into multiple diagnostic categories, so designs with over 2 possible diagnoses were rare. This is really in contrast with the unmet clinical needs which I just outlined at the start of the talk. We do realize that this is related to the design of the available data sets, because typically the data sets focus on one type of neurodegeneration rather than a mix of different types of neurodegeneration. Another point is that often studies lack validation in real-world data, and Esther Braun will discuss this in more detail later on in the symposium. So coming to the end of my talk, I also want to have a critical look of the possible role of clinicians, and how sometimes clinicians may also act as a barrier for the introduction of AI tools in the memory clinic. Perhaps one could say that some clinicians may have reservations about the introduction of AI tools in the clinic because they lack trust in these types of AI tools. We also noted that in general, AI training in medicine is limited. A second concern which I want to raise here is that AI, as you know, can sometimes be a black box. And as a clinician, it's very important to know if the AI tool generates a specific diagnosis, that we can evaluate which variables are driving and leading up to this specific diagnosis. And so from my point of view, explainability will be a key factor to convince clinicians that AI tools are detecting meaningful substrates of neurological diseases. So to conclude, one of the key questions in the memory clinic which AI can play a role is differential diagnosis of neurodegenerative diseases. I think multidisciplinary teams are ideal to overcome such challenges as to implement AI tools for the memory clinic. And the potential roles I see for clinicians are to identify unmet clinical needs in the memory clinic, to interpret study results, to contribute to real-world data collection and validation. Also, I think it's worth our while to encourage AI training for clinicians so they can adopt a critical but open-minded stance towards AI tools. So I want to thank the audience, the members of the Demon Network, and my colleagues from University of Antwerp. And here you can find the QR code to the systematic review. Thank you.
Thanks so much, Rose. That was great. After that introduction to the issues and challenges of AI, we're going to move on to a video presentation from Professor Yong Liu. Professor Yong Liu is a professor at the Beijing University of Post and Telecommunications School of Artificial Intelligence. He's an associate editor at the Journal of Alzheimer's Disease and is a member of the Center for Excellence in Brain Science and Intelligence Technology at the Chinese Academy of Sciences. His work focuses on understanding brain networks in neurodegenerative diseases, and particularly Alzheimer's disease. Unfortunately, due to travel restrictions and quarantine issues, he can't join us, and it's a real shame because I've known Yong for many years, since he came and visited Cambridge about 10 years ago now. He's a warm, collaborative colleague. He's got a huge smile and a great sense of humor, and I think we're going to miss that. But in this presentation, I think what we see is the best of him as a high quality and really thorough scientist with a focus on the translational aspects of machine learning. I apologize for the sound quality in this presentation, but I hope what you get from it is some of how we can apply these AI machine learning methods for use in this practical way, in particularly looking at MCI and Alzheimer's disease.
Dear all, as we all know that the Alzheimer's disease is a program as specified by the NRAA research framework. Biomarkers for Alzheimer's disease are grouped into those A-beta, tau, or neurodegenerations. That means the ATN criteria. But for most countries worldwide, the PET and CSF are not easy to be achieved. Meanwhile, the MRI has become very popular in different hospitals. So it will be great if we can identify robust imaging biomarkers based on this non-invasive technique. We all know that we can get different modality of brain imaging, such as the structural MRI, differential MRI, function MRI. So if we want to get more detailed information searching biomarkers for Alzheimer's disease, we need hard work on developing imaging analysis of these measures. And that means we need more artificial intelligence network. In fact, we can get different information or different features from this imaging, such as the brain activity, brain network, the brain matter volume, the methods on white matter fibers. We can learn the impaired mechanism, the early diagnosis, the personal prediction with these features. If we can extend these frameworks from one side to multi-side, we will get robust features for early individual prediction of Alzheimer's disease. There are three primary features character a biomarker. 1, objective and qualitative. 2, reproducible and serializable. 3, neuroscientifically interpretable. However, we have performed many group comparisons based on the data from one single site. Here, I do not mean that this kind of analysis are not important. However, I want to argue that we should pay more attention to independent cross-validation and individual prediction with the machine learning method. For Alzheimer's disease imaging biomarkers, we can investigate the producible qualitative features from the local brain regions, the whole brain, and the brain networks. Many excellent studies have been published in the past years. Convergence evidence shows that we can get good models from these scales. I will give some examples based on our latest work in the following. Remember, one cannot make bricks without stone. That means we cannot get any features if we do not have good data. Hence, all the following examples work on an in-house data set and a public identity with around more than 3,000 subjects. The Alzheimer's disease is known to target hippocampus regions. Therefore, the first example is about the hippocampus radiomics features in Alzheimer's disease. The hippocampus undergoes microstructure changes before severe atrophy, and pathological changes such as neurofibrillary tangles or A-beta are not directly detectable at the current resolution of the clinical MRI. Thus, novel MRI analysis that yield more incredible information about the changes in hippocampus would be a significant contribution to the Alzheimer's disease. The radiomics features, a method for text analysis, provide more information about the first, second, and high-order morphological features for Alzheimer's disease. So, the radiomics features provide increased precision in diagnosis, assessment of prognosis, and prediction of therapy response of the Alzheimer's disease. The first aim of this study is to explore whether the hippocampus radiomic features with a reproducible change setting can serve MRI imaging markers for AD using multi-site MRI. Here, there are around more than 700 subjects from 6 sites in China, and we also include an independent data set from Italy with more than 1,000 subjects were included to further assess the reproducibility and generalization of these findings. The second hypothesis is that these redomy features or classification output have a solid neurobiological basis. Therefore, I assume premonitory promise as a potential marker of Alzheimer's disease. For this purpose, we investigate the neurobiological basis of the artifact hippocampus redomic features by relating these features to other variables, including the MMSE, ApoE, CSF A beta score, and also the progression of the disease status of the high-risk subject, that means the mild cognitive impairment subject. Hippocampus redomic features different among the Alzheimer's disease, mild cognitive impairment, and normal controls. Notably, this result showed that the difference map was significantly related between the Alzheimer's disease, between the adenine and the health database, which validated the reproducible of the redomic features. Secondly, the cross-validation analysis suggests that the hippocampus redomic features can serve as a robust biomarker for Alzheimer's disease. Thirdly, we can get that for the high-risk subject with more than 5 times vision, the change in different redomic features had a high uniform variation trend with the change of the cognitive ability in the progress mild cognitive impairment subject. And we all know that in the Alzheimer's disease subject, the atrophy has been shown to start in the medial temporal lobe and then spread to the posterior temporal lobe, parietal lobe, and then eventually to the frontal lobes. It will be great if we can evaluate which region provide a key contribution to the imaging by. These days, the deep learning models make artificial intelligence more popular in Alzheimer's disease prediction. Traditionally, we input imaging features in, and with the predictions go out. There exists a black box for this framework. However, at the doctor's office, we all hope that we can open the black box and know the exact cause of the Alzheimer's disease. In another work 2 years ago, we developed a 3D attention network that can not only capture imaging biomarkers with attention mechanism and can advance the diagnosis of Alzheimer's disease based on structural imaging from cross-validation, important reason, and neurobiological basis. The producibility will evaluate user cross-validation on in-house stage and the public adenine stage with accuracy around 87%. And more importantly, the effectiveness of the 3D attention model was further validated by its good performance in predicting the mild cognitive impairment subject who progress to the Alzheimer's disease with 3 years with accuracy around 71%. Significant association between the classification output and clinical characters of Alzheimer's disease provide solid neurobiological support for the 3D attention network model. And in a short summary, our findings highlighted the potential for structural brain imaging to provide a generalized and neurobiological interpretable imaging biomarkers for Alzheimer's disease. And we all know the Alzheimer's disease is associated with disruption in brain activity and brain connectivity, which suggests that the Alzheimer's disease may be a disconnection syndrome. Follow a complex analysis steps, we found that relative to the normal controls, Alzheimer's disease subject was associated with the significant reduction in functional connectivity and local activity in deformal network and singular gyrus, and also along with the increased connectivity or local activity in the prefrontal lobe. Leaving without cross-validation, established that diagnosis status and the clinical scores could be predicted with high accuracy. And collectively, our findings highlight the potential for a reproducible functional brain imaging biomarkers to aid the early diagnosis of the Alzheimer's disease. More importantly, we found that with these impaired connectivities, we can cluster the ultimate subject into 4 subgroups using a non-negative matrix fraction method. And we also found that this difference in connectivity and the difference between the ultimate disease subtype was found in cognition, structure methods, and cognitive decline patterns. This comprehensive result offers new insight that may advance precision medicine for Alzheimer's disease. This finding shows that the brain imaging features can provide believable and robust information to discriminate the progress of Alzheimer's disease. And also the classification analysis result provide encouraging evidence for us for using the brain imaging feature as a potential biomarker for clinical application in Alzheimer's disease. Also, the change brain imaging features was strongly associated with its neurobiological basis. For imaging biomarkers of Alzheimer's disease, we still have a lot of work to do. Firstly, many researchers have realized that the reproducibility is one of the keys for imaging biomarkers of Alzheimer's disease. And now they start to call for more groups and countries to work together to provide a real cross-validation for certain biomarkers of Alzheimer's disease. We should admit that most of the previous studies, the data are carefully controlled for different variants. However, if we want to put the lab research model to a real clinical application, we need to validate these models with real clinical data. We have made all the toolkit open on my GitHub. Please do not hesitate to contact me if you have any questions. And here, we want to argue that if you have any good idea, good data or code for Alzheimer's disease imaging biomarkers, you are welcome to join us to study our data. Lastly, I want to say thanks to all my collaborators, and thanks to all the fundings, and also thanks for the chairs. Thank you for your attention. You can follow me on the following posters, Google Scholars, and Twitter. Thank you. Thank you again.
So we'll move on to our next speaker. Dr. Andre Klempeer is a senior community engagement scientist from DNA Nexus. He studied at the Czech Technical University in Prague, where he completed his PhD before moving into industry as a bioinformatics engineer, working on machine learning and statistical projects with various large data sets of single-cell metagenomics, proteomics, and systems biology data. He moved to DNA Nexus just over a year ago. DNA Nexus are one of the leading companies in cloud computing and bioinformatics, particularly in the field of genomics, but increasingly in neuroimaging, making particular use of the UK Biobank dataset. Their aim is to bring data together to tackle the world's most exciting opportunities in human health and beyond. Welcome, Dr. Andre, and we look forward to your talk.
Thank you very much for the introduction. Good morning, everyone. I would like to talk in this presentation about infrastructure challenges, and I would like to specifically touch on machine learning models and how we can deploy these models on the cloud. So the title of this talk is Machine Learning in the Cloud is Future-Oriented Solution. Again, I will just briefly introduce myself. I would like to say again that I work for DNA Nexus. I'm senior community engagement scientist or specialist there, mostly focusing on genomics and imaging/neuroimaging data. And in this talk, I would like to cover the following topics. I will very, very quickly introduce DNA Nexus as company and the platform where I did the experiments, computational experiments for this talk. Then I would like to talk about biobank as a large-scale data set, because this is the data set I used in my experiments. We will cover, from the technical perspective, some differences when working on the cloud and mental models and ways of working on the cloud. And then I would like to specifically jump on two simple scenarios, machine learning scenarios, and the first of them will be image augmentation using MONAI library, deep learning. And then actually we will use something which is called image-derived phenotypes on the UKB data, UK Biobank data and UKB RAP, and do some training of models on that and show some results. Perfect. With that being said, I would like to first introduce DNA Nexus as company. DNA Nexus is a US-based company providing a clinical genomics data platform. We have many customers on the platform, but importantly, UK Biobank is one of the we are actually strategic technology partner of UK Biobank, delivering and powering UK Biobank research analysis platform. And that's the tool, that's the platform where I did my experiments, and this is the thing I will be introducing and talking about. What is the problem statement? Actually, or like current challenges in the AI/neuroimaging field are the following. Basically, the neuroimaging-based machine learning and AI, typically, a typical issue, typical problem is lack of large data with rich phenotypic information. Also, it's general, it's kind of general knowledge. Actually, we all understand that the machine learning models work best with lots of data, with massive data sets, and also not only massive data sets, but also high quality data as inputs. So let's say thousands to millions. And another issue with reproducibility. Let's say another issues are related to storing all the big data and massive data sets in some centralized location, and making everything simply easy for large teams to perform analysis and collaborate. And let's say pre-install software, then reuse the software later in your future analysis. So, and what we can do, actually UK Biobank datasets provide solution to one of these issues. UK Biobank is dataset with rich phenotypic information, and they collected data from 500K people. If you attended the awesome talk yesterday presented by Professor Carla Miller, I mean, she helped me a lot in introducing this topic. But yes, this is very, very large data set. It's collecting data from UK population, age between 40 and 69. And what is important to say here, that this data contains many fields, many bulk data, many file formats. It's collecting data about lifestyle, physical measures, genetic or genomics data, and importantly, imaging, various modalities of imaging. And these will be the inputs or sources for our experiments. In this case, I would like to specifically talk about UK Biobank Research Analysis Platform, which is a platform powered by DNA Nexus. I made all the experiments presented here, or I performed all the experiments presented here in this environment, on this platform, in the cloud. And just to quickly reiterate, or just to quickly give you an introduction to what this platform does. Actually, it's a secure research platform hosted on AWS London region. It's bringing the researcher to the data, making data access and compute more widely accessible. UKB RAP, UK Biobank Research Analysis Platform, allows secure and fast analysis of UKB data. So that's one of the options how you can access UKB data. And importantly, again, for us, it has a lot of brain imaging data, various modalities. So if you want to know more about it, all the protocols, processing pipelines, data file formats, and its documentation should be available publicly. So you should be able to find it. And brain data is a key part of imaging, with over 50K participants scanned to date. And again, I'm referring back to presentation by Professor Carla Miller yesterday. The presentation was about how to scan 100K actually, so this is progressing in time. Right, so when we work on the cloud, not only on the DNA Nexus, but let's say more in general, what are the options typically for working with data, how you can do your analysis, more advanced analysis, or even machine learning analysis. Here, let's say specifically on DNA Nexus, and this would be similar for other tools, other platforms, there are typically some tools already pre-installed, already available for your analysis. You can work with already some pre-ingested data, typically, or with bulk, I mean like raw data, or you can typically write workflows in the specific neuroimaging field. That would be, let's say, workflows written in WDL, or also called WDL, or tool NiPipe, which is then incorporating FSL or FreeSurfer, or you can work with JupyterLab. Yes, or you can use many other options, or even you can install software packages in these different environments and bring your own tools on the platform to the cloud. I made the experiments in a JupyterLab environment. So, and what are the most, what are the differences between your local computations, or let's say working on your company, university, high-performance clusters versus working on the cloud? So here, let's review some basic setup, basic flow. First, on the cloud, you would need to request worker, because every time you run a fresh new machine, remotely, so first request worker, which is also called instance. This will lead to getting your temporary worker. With that, you will also sometimes need to provide machine learning environment. That means this will specify some pre-installed software for analysis. I mean that this step will run a cloud. Will ensure that the cloud worker is launched and, in this case, managed by DNA Nexus. Then, really importantly, what you will need to do, because this is like really a machine with with just pre-installed software, but there are no your custom-made scripts, no data available for your analysis. So in the next step, you will need to transfer your scripts as well as data from some permanent storage to your worker. So first, let's say transfer scripts from permanent project to the worker, I mean temporary worker. Then also you will need to transfer data from your permanent storage to the worker. In this case, it could be subject-based image in zipped format, or it could be, let's say, Nifty image. Once we are done with that, you can do some pre-processing steps to, let's say, unzip the image, and then you can execute your pipelines, your analysis in the cloud, train your models, or you can also apply already existing models to new unobserved data. Then, as a last step, you will certainly need to save the results back to permanent storage. That means output transfer or output your results back to project storage, to some permanent storage. And also with that, there are possibilities on the cloud to version your software, version your models, machine learning models, or even create snapshot of your tools you installed on the temporary worker. So these are the kind of best practices for working on the cloud. Right, so one example of running such model. Let's say here we would like to run machine learning with GPUs, instance type with GPUs, and we are working on the UKB wrap from within Jupyter Lab environment. So what we can do, typically on the cloud, we will need to select instance type, particular instance type we are interested in, which is all the capacity to do your computations and intensive computations. So in this case, we used suffix with underscore GPU, which defines GPU computations with some specific memory and number of cores. And when this is requested, once this is installed, we can confirm the installation with some specific command. So with this setup, we can run GPU intensive computations. And typically on the cloud, we have some tools already available. So in the case of UK Biobank research analysis platform, we have many tools available, let's say, for genomics, for translational informatics, also statistical analysis, but then more specifically for neuroimaging, we can, let's say, use SniPipe with FSL and FreeSurfer, and also machine learning frameworks such as TensorFlow, PyTorch, and many, many more. And I made these, I made my computations and experiments on GPU, so this is compatible. Okay, so with that, let's continue with machine learning scenario number 1, and it's image augmentation using MONAI deep learning. So what is MONAI? It's a library, deep learning-based library for a specific task which is called image or data augmentation. I will talk about it in a second. So basically, it's PyTorch-based framework for deep learning in healthcare imaging. It's a really, really fast way and good for prototyping to build deep learning pipelines, and that's an option how we can test deep learning pipelines on the UKB wrap. It can be easily installed in the cloud. I did it just by running a couple of running commands. It can run on GPU. And what are the basic MONAI tasks? It's a classification, very well known in deep learning space. It's a segmentation. It's a data labeling, yeah. And in this case, it's data augmentation. So more specifically, what you can do with MONAI in terms of data augmentation, you can, for specific cohorts with, let's say, very simple sample size, very, very, very limited sample size. It could be cohorts for Parkinson's disease or Alzheimer's disease or other aging or other neurological disorders. You can then enlarge your data set and prepare more training examples to even improve your models and its training. So in this case, MONAI transforms provide an easier way to augment data, since it doesn't require model training as long as you don't apply too many transforms. So then, as a result, images will look realistic. So what I did, I just installed everything in the cloud. It was relatively simple to do all the steps. And in this case, I'm just showing one example of a slice of the UKB data, brain data, and basically you can compose multiple transformations, such as rotation, cropping, zooming, translation, and combine everything together into one final transformation. And then you can also fine-tune your models. So yeah, so basically I just tried these transformations and created derived image with no interpretation in this case. It's just as example of such installation. So in the machine learning scenario number 2, we can train the model on something what is called image-derived phenotypes. On the UKB wrap, or UKB data provides data in tabular form, which has form of database, and many features are available, basically computed by FSL and FreeSurfer. I would like to refer here to FSL Oxford Group, this team develops pipelines for processing and producing data. So this was already ingested, so I can use it directly in the cloud on the UKB wrap. And so for each image, we have a set of features, a large number of features to be then used in my machine learning experiments, or let's say GWAS, if you are interested in genomic space, if you are genomics or bioinformatics scientist. And here, I just used a graphical interface, which is called cohort browser, to apply some filters, and in order to specify my cohorts. So yes, in this case, I am focusing on data from vSurfer and FSL, talking or considering some volumes and features related to white and gray matter. So yeah, I can here apply simple filters. So yeah, so this led to specifying my cohort. So also, in the UKB data, there is a series of information containing International Classification of Diseases version 10 information. So you can then, let's say, filter or check groups of participants which had, let's say, dementia parameters reported or something what is related to Alzheimer or Parkinson's disease and so on. So actually what I did some simple training, just example training. It's a model developed, let's say, in half of hour or 1 hour. So we can train a model, everything is running on the cloud, to predict age, because brain age or aging-related studies are really topic at the OHBM. I saw many posters yesterday which are trying to develop such models. So we can explain the age by several brain volume features on the UKB RAP data. So my model was trained using just neuroimaging process data in a tabular form. Everything was defined in GUI, but as well as you can do it programmatically in JupyterLab. And I used approximately 3K participants in my selected cohort, and applied tenfold cross-validation, and I did some evaluation by the following criteria, following metrics, which is Pearson correlation coefficient, R squared, and mean absolute error. And then I fed the data into Lasso model from scikit-learn. So you can see that on the cloud, I was able to use, let's say, Python packages, and one example is scikit-learn. So yes, and then importantly, what is the what is the big advantage of working on the cloud for reproducibility, and it could be also open research? I can then save my notebook, save the models with particular versions, with all the metadata, and also save the whole environment to the permanent project on the cloud, and then, let's say, collaborate with my team or share everything with my team and my colleagues, right? Yeah, perfect. Here is only preview of some correlations with age at recruitment, yes. And also some plots which were developed or which were computed or which were done in the cloud, yes. So let's say PCA plots, or with no interpretation here, and also a cross-validated results where each color corresponds to one training set. Yeah, just to summarize, in summary, we saw that MONAI transforms provide an easier, faster way to augment data compared to generating synthetic data. We were talking about reproducibility and working on the cloud and how to deploy models here specifically in UKB RAP, which is platform powered by DNA Nexus, and a way how to work with UKB data. And this can lead to better model versioning and reproducibility. And as a next step, let's say, raw data can be annotated with the results of machine learning analysis, actually accelerating the work of clinicians and translational researchers and translational informatics researchers. So at this point, I would like to say thank you to my DNA Nexus colleagues. I would like to say also thank you to you, to the audience, and I will be happy to answer any questions you may have in this regard. And last but not least, I would like to say thank you to UK Biobank. Application ID presented materials were carried out using UK Biobank application number 46926. Yes, and we also thank the participants in the UKB imaging study. Thank you very much.
Many thanks, Andre. That was great. So hello to everyone who's come since 8 o'clock. Nice to have you here. So we've heard from Rose about the sort of challenges of AI for clinical medicine. We've heard from, or maybe perhaps it's read from Yong about the methods that are appropriate. We've heard from Andre about the sort of platforms that will permit the scalability that's required for this sort of clinical AI neuroimaging. And now we're going to hear from Esther about how far we've got in actually translating these tools into the clinic. So Professor Esther Bron is Assistant Professor at the Department of Radiology and Nuclear Medicine at the Erasmus University Medical Center in Rotterdam. From being Young E-Scientist of the Year in the Netherlands in 2018, she's gone on to develop international collaborations, including the Progression of Neurodegenerative Disease, or the POND project, and has developed the novel DEBM model for assessing the progression of neurodegenerative disease from cross-sectional data. Esther's work really focuses on how to get the most value from big data and AI in neurology for the benefits of patients and doctors. And just a quick note, we'll take Q&A at the end on the sort of panel session, so please have a look at the phone app and put any Q&As that you have there. So Esther.
Yes, good morning. Thank you very much for the introduction. And let's see how this works. Yes. So I have no financial disclosures myself, but one of the companies I mentioned is a spin-off of my institute. So in the light of this symposium, as Tim already explained, we are very interested in how to get AI out of the lab and use it for diagnostics in the memory clinic. So the previous two talks talked about the technology that we have. In the first talk, we heard what the memory clinic, what clinicians need from AI, but there is still a gap in between those two. And I think one of the main elements of this gap is validation, clinical validation, and that is what I'll go into in this talk. So first, a short recap of what technology we are talking about. So we're talking about AI, mostly machine learning, based on multimodal data, so large-scale MRI data, in combination with clinical information of patients, cognitive testing, lab testing, to train a model on a large data set to make a diagnosis or a prediction of dementia. And this is a large research field which really took off from the year 2008 with the first publications becoming available related to large-scale data starting to become available. And as Rose already mentioned in the first talk, we recently did a review, a survey of papers in this field. So here you can see how they are sorted in different types of methodological categories. And I want to highlight that the state-of-the-art performance for these methods distinguishing Alzheimer's disease patients from healthy controls is around an area under the curve of 92%, which is quite high, but it's still not used in the memory clinic. So one point, as Rose mentioned, so this distinguishing dementia and of Alzheimer's disease and controls is not the most relevant clinical question, but also clinical validation. So how do these tools actually work in real patients on real-world data is an open question. And I would like to illustrate this based on something that is being used or starting to be used in the memory clinic, which is AI for quantification of MRI. So here, these types of AI methods, so AI for quantification, they apply machine learning or image analysis to obtain volumes or other biomarkers, but mostly volumes from structural MRI. That is what's being used in the memory clinic at the moment to extract volumes of white matter, gray matter, specific brain structures such as the hippocampus. And to go more into that, I will first take a step back to the traditional role of MRI in the memory clinic. So traditionally, imaging has been used to exclude other causes of cognitive impairment that may be treatable, so for example, a stroke. So that was the first role of MRI, and in the last decades, the role of imaging MRI became larger, but also on finding the underlying cause of the dementia syndrome. So by identifying specific patterns of atrophy and finding the severity of vascular lesions in the brain. But what we like to go towards in the future is to get even more sensitive information out. From these large, high-dimensional MRI scan, we can do better than getting just large structure volumes, and so using voxel-wise high-dimensional information and combining with other markers to get towards diagnosis in an early prodromal stage of a dementia and predicting of conversion of dementia in patients with mild cognitive impairment. So how it's currently being used is visual assessment by a radiologist of MRI scans. So the radiologist finds patterns of atrophy, something is happening. So the radiologist is finding patterns of atrophy using scores. So the mediotemporal lobe score and the Fazekas score. And then I hope I'll get my slides back soon. Yes. So visual assessment is what's currently used in memory clinic. But what is currently making its entrance is AI for quantitative assessment of MRI, which includes like automated tissue segmentation, so segmenting the brain into white matter, gray matter, CSF, and also finding specific structures, quantifying their volumes, and plotting them against normative reference data. So this is an example from the Rotterdam study, where you can see how brain volume changes over age for men and women. So these data from large data sets can be turned into percentile curves, and then the data, the volumes of an individual patient. So here you see it for whole brain, total brain volume, but this can also be done for separate structures to assist the radiologist, but also the full diagnostic team into making a diagnosis. So taking account of age and what is normal for a patient at a specific age. And so there recently was a survey from the European Neuroradiology Society asking neuroradiologists who of them is using such software, and the majority doesn't use such software, but some of them do. So a small percentage always, and some of them only in specific cases, and then if they do, they use hippocampal volume, total brain volume, or lobal volume. And the reasons for not using it are that they don't have the software available to do so. It might be too time intensive, or they don't have the expertise to use such a software. But there are real potential benefits of using a quantitative assessment of MRI. So it is automated and reproducible. So the software will always create the same numbers. You can take account of age by comparing to normative data, and it could be more consistent across levels of radiologist experience. But cons could be that it's not integrated yet in the daily clinical workflow, so it might take extra time, and there might be a lack of evidence on clinical and diagnostic efficacy. So we're going to look into that. So about software not being available, so there's currently a lot of companies, here you see a wide selection of them, that have such software available on the market. And another survey was done by my colleagues from Erasmus MC in collaborations with colleagues from University College London, in which they assessed all softwares that are FDA approved or CE marked in a systematic review. And these are 17 softwares that target neurodegeneration. They do this first automated brain segmentation. They have some sort of normative reference data, and they present the results in a report for an individual patient. And then they evaluated in this systematic review these softwares according to the Quantitative Neuroimaging Initiative framework. And they separate 3 types of validation that should be done for a method to be used in clinical practice. So that's first technical validation. And technical validation is, does the software do what it promises? And this is what is needed to get it CE marked or FDA approved. And so it looks into scan-rescan results, or how does it compare to state-of-the-art methods. And the second step is clinical validation. So what is the diagnostic accuracy in the patient group? How does it impact patient management? How does it influence the confidence of the radiologist or of the physician? So that's the step of clinical validation. And then the last step of the validation should be validation of the software when it's already used. So the validation of the integration into the workflow, assessing what is actually the benefit to the patient of using such software, how does it affect reporting time, and how is it perceived. So the survey looked into all of the validation papers that are published related to those softwares. So of the 17 companies, at least 11 of them had one or more technical validation papers. 7 of them had at least one clinical validation paper, and there were no in-use workflow validation papers published. So the total number of studies of papers, published papers, was 62. You can see the majority is technical, some clinical, and no workflow validation papers. And then regarding to this clinical validation, so does MRI quantification actually improve diagnostic accuracy in clinical practice? And these papers actually have very limited data on that. So it suggests a modest improve in diagnostic accuracy and a modest improve in confidence of the radiologist. And that seems to be dependent on the type of dementia, on the experience of the rater, and on the different types of software. So how steep is the learning curve for a software? But more insights on this are definitely needed. So coming back to this list of pros and cons. So technical validation seems to be being done well. So softwares are automated and reproducible, and such things allow to take account of age because of the normative data. But we don't know yet if it indeed become more consistent reporting. Also on integration in daily clinical workflow, not much is known yet. And the diagnostic clinical efficacy, we need more data to give a full answer to that question. So in conclusion, so we took AI for MRI quantification as an example, so that has a high potential benefit in the memory clinic. But the available tools, they are there, but need more evidence for real-world application. So there's definitely a need for more clinical validation studies. And I think in the future, when we go to even high-dimensional MRI markers, other types of MRI sequences maybe, or combination with other markers, we can learn from this and maybe take on these types of validation earlier to get towards early diagnosis and prediction in dementia. So thanks to my colleagues, and thanks to you a lot for your attention.
Well, many thanks, Esther. That was great. So now we'll move to the panel discussion. There's been quite a few questions come through, so thanks very much for that. We'll work through. I'll just address the first issue first about the recorded sound, and I apologize for that. A huge amount of work goes into putting these presentations together. Jong is very aware that his accent in English is not the clearest, even without the sound issues. But he put together, I thought a beautiful set of slides, well referenced with papers and so on to line up. So I do hope you got something from that, despite the sound quality. So next, the question, maybe we should start with Rose with this. How much do clinicians really care about explainability? Wouldn't they prefer a more accurate black box? Oh, if the person's here who answers that question, could you ask that question? Give us a wave, thank you.
Yes, I think it's a super important question that we really have a stance on this. I'm going to be clear on my own personal view. Others can comment later if they wish to join. I think it's super important to have explainability. And that's for several reasons. The first reason is that with the current state of AI, when you think about training datasets, testing datasets, validation, it is clear that we can never have a 100% accuracy. Even if you would have a situation where you could ideally classify between, for instance, these three common types of neurodegenerative diseases like Alzheimer's disease, frontotemporal dementia, Lewy body disease, that would be great. I don't believe that is possible already because there are large individual differences. They are at play and they play a great role in healthy individuals, and I think their importance is really much underestimated in the evaluation of neurodegenerative disease. So for that reason, even the discriminating between these three major types of neurodegeneration is not feasible yet because we are lacking important knowledge of neurobiology to do so. Furthermore, a second point is that I haven't addressed rare diseases. In neurology, we are encountered with sometimes rare diseases, which even as a neurologist, you see once every 10 years. If you put that into the perspective of training data sets and testing data sets, your training data set will not be rich enough with all these rare kinds of diseases to accurately detect them and be able to diagnose them with AI tools at the current time. So that's from the clinician scientist perspective. A second perspective I would like to add here is the patient perspective. Imagine that you go to your physician with memory complaints and you get a workup, you're scanned, and there's an AI tool that looks at your scans, and your doctor tells you, I'm sorry to tell you, but you have an incurable neurodegenerative disease. That's shocking enough. But if your answer to this, which is a very legitimate answer or reply, is, yes, but can you tell me why? And then your physician would say, well, the AI tool tells me, but actually I'm not sure why the tool is telling me so. We don't have the variables. I don't think that that's an acceptable answer for a patient. So that is my take on this. I don't know if anyone else would like to comment.
I think the next...
Very quick answer. Yeah, I think I completely agree. I think doctors are naturally skeptical, and we know that tests get things wrong, and when they get things wrong, we want to know why. Yeah.
And patients are skeptical too. So there's a lot of questions on data protection. So how are these issues handled with working with sensitive patient data on the cloud?
Well, yes, typically cloud providers and the platforms have really many standards and many regulations for data protections. So typically the criteria are met in terms of data security and similar aspects. I can at this moment I can comment on or about the UKB RAP platform. In this case, UKB data. They are participants from the UK Biobank, and these data everything is anonymized. It's not transferable between projects. So it always has some uniquely generated specific EID or participant ID, so you cannot like recognize or assign patients between projects. So you can do just like do the computations on average, or yeah, that's the point. But yeah, just short answer. Typically, AWS, DNA Nexus, other cloud providers have really secured standards and meet all the regulations for data security. Yes, yes. But it's still like developing. It's still progressing. Yeah. We can talk more maybe offline. about the next details, but yeah, that would be the answer for now.
So I guess the more general question is, if and when we take more advanced AI to the clinic, how do we go about it? Does a single lab provide all the information to the clinics? Do we do it in a more reproducible, standardized manner? Do companies step in at that point to provide this service? We have these kind of services for blood labs, etc. So I'd be curious to hear from the clinicians on the panel, as well as maybe from Andre on these issues.
Esther, do you want to answer that?
Yes, sure. So I think companies can provide the software, will provide the software and make sure it does what it promises and show that it works in the clinic, but it will remain the clinician that is responsible for making the diagnosis and communicating that to the patient. So I think that comes back to the first question, that the clinicians understanding what they're working with, what they're doing, and being critical to outputs is key.
I think you've got to think about what data you're sending. Send the minimal amount of data that is necessary for that to the cloud for that analysis to be done, but making sure that it's not the wrong data that comes back. Making sure that ID goes all the way through with the patient, I think, is really critical. So there's another question which. Yeah, so I suppose we sort of covered the other one a bit about the sort of DNA nexus compared to the HPC. I mean, they're sort of similar but different. I mean, HPC is at the DPUK, for example, is much more, or at universities are much more for sort of the academic side of things, and won't have those same regulatory ISO standards. There was another question I was just going to. Oh yes, that was the one. So how do you handle comorbidities in dementias, which post-mortem is not an exception? So if the person's here who answered that, could you give us a wave? I don't know. Let's hear whether that was online. Rose, you want to answer that? So how do you deal with comorbidities in this population?
Well, actually, it's a super interesting question. I think it also circles back to the type of data sets that we are collecting right now. Typically, as we've identified in the systematic review, a lot of cohorts are collecting data from controls and patients with one specific type of neurodegeneration. So one of the suggestions was to have more designs with multiple instances of neurodegeneration, but actually one step further is something that Esther has also touched upon, is that we're actually looking for real-world data. And of course, in the real world, you often get these mixed type of pathologies. There are several fundamental clinical questions that also need to be answered. How the relationship between the different types of pathology and the actual impact on cognition is, which is a more fundamental research question, but also for the implementation in the clinic, I think the collection of real-world data will really be needed. And I think, Tim, you also are leading a project on this. Maybe you can also comment on the real-world MRI data collection, for instance.
Yeah, I think it's really critical. I think if you're just using ABNI, you can't really answer questions about comorbidities because they're just excluded from the data. So I think that's a real challenge at the moment. So certainly in the UK, sort of leading a project called Quantitative MRI in NHS memory clinics, where we're trying to collect data from everyone who comes through the clinic across sort of 6 different sites. And what you find, as in most memory clinics, just less than half the patients have Alzheimer's disease. So if you're just using ADNI, you're not going to be able to capture those comorbidities. Your results won't be relevant to more than half the people who come to the memory clinic. So I think there are really big challenges, actually. So for me, anyway, real-world data is absolutely critical for validation of anything that we generate in the academic space.
Yes, because regarding to methodology that is currently available, I think hardly any do take comorbidities into account and mostly focus on Alzheimer's disease versus it's mostly ADNI focused. So data sets is key, and I think there's a growing interest from method developers to use that data and take it into account. finding new ways of modeling, also taking account of vascular effects, for example, on top of neurodegenerative pathology.
Yeah, and in Canada, we're collecting the COMPASS ND data set, which is not any pure form of dementia. So it's different dementias, but with all the comorbidities and the spectrum versus like a very pure form of a dementia.
Unfortunately, we're out of time, which is a real shame, because we've got loads more questions to go through, but please do come and have a chat afterwards. And a huge thank you to our speakers for very varied but fantastic presentations on this very challenging issue. There's still much to resolve. And thank you for the questions in the audience as well.